So we are in Statistical Rethinking, second edition, chapter 13, and we're on question 13M5. Okay, so we are going to modify the cross-classified chimpanzee model of our M13.4. And so we'll see that model here in a minute, so that the adaptive prior blocks contain a parameter, gamma bar, for its mean. Okay. So what has this done? What has this done to the model? So we're going to compare the modified model with the original model. Okay. So let's kind of get our bearings around what's going on here. So so this chapter is discussing, I guess, several things, and one of them are these multi-level models. And the thing that makes a multi-level model is the existence of these hyperparameters, okay, or hyperpriors as it's denoted here. Okay. And these are, so how do these work here? So, so we have our normal model that we've been used to using, but a parameter, in this case we'll just take a separate parameter will be estimated for each actor in our data set. Okay, and so we get a prior for that. All right, but now that prior itself has priors. Okay, the parameters of that prior have priors. Okay, so what that does essentially is it says that yes, we're going to estimate separate A parameters for each actor, but each one of those intercepts are going to come from a different distribution. And what this has the effect of doing is kind of pulling these individual estimates kind of towards each other according to the distribution that they are being parameterized as. Okay. And so that means that this prior right here, or that each of these priors is not actually set, right? It adapts according to the data. Okay. Now, how does it adapt? It adapts by learning good values for the hyperparameters, and those hyperparameters themselves have distributions. So that's really just a recap. Hopefully, you're following along in the book, and that will just kind of help place in context what's happening here in the question. Okay, so so this is the model that is found in the book right here, M13.4. I've just copied and pasted it. And what we're supposed to do is we're supposed to modify this right here. Okay, and we're supposed to modify it by instead of giving it a mean 0. We're supposed to give it a mean of gamma bar, or G bar, which I've done here, and then giving G bar a prior of that's identical to A bar, 0 to 1.5. Okay, and then what we're going to do is we're going to compare the two models and try to see what including this additional hyperprior has done to the model. Okay, so I've already ran this, so we don't have to look at it again. We are going to come back to this little part right here, that little chunk at the end of the model, and this, as well as this chunk, which kind of gives a summary of how well the chains ran. Okay. But the first thing to do, I think, is to just compare the pricey outputs here. Okay. Now, there's a lot of things, there's a lot of parameters, and so it's going to be a little bit difficult to go through each one of them. But instead, let's go all the way over here to the right-hand side to the R hat statistic and the ESS, or effective sample size. Okay, and remember the R hat is kind of a value that tells you kind of how well the model converged, or how well the chains kind of intermixed, and the ESS is the effective sample size. Okay, of your Markov chain. All right, so values of R hat close to 1 are better than ones that are farther away from 1, and ESS values that are higher are better than ESS values that are lower. And so if you take the time to go through and compare these, you'll see that they're pretty close. There are, the two models are going to be both reasonable, I should say, but the R-hat values in the first model are better, slightly better, than in the second model, right, where we modified the model, right? You see some 1.03s here, a couple of 1.04s, etc., and you don't see any of those in the first model. And then you'll also notice that the effective sample size is typically much higher in the first model than in the second model, right? So many of these have values in the 200s, and most of these up here, they only go to as low as, in the 400s, mid 400s about, okay? And so that maybe suggests that the first model is running better, for lack of a better term. And we can actually see that being the case, because if we go to the second model, again, the modified model, we note a few things. One, we see that it takes 40 seconds to run, whereas the first model took 10 seconds to run. All right? The second model had 45 divergent transitions, as well as 54 maximum tree depth limits. The second one here is not really a problem in many circumstances, but but it just gives you an indication of how poorly the model ran. If you want some more details on that, of course, you can go to that link there. It gives a better explanation of what I'm going to give here. But if we go up to the first model, we see that there were a few divergent transitions, but only 4, and there was no tree depth limitations here. Okay, so it really does seem that the first model was running better. Does that mean that the inferences or that the parameter estimates are not valid in the second model? Well, no. If you go through each of these, and I'm not going to do it here just because it's a little bit hard to get everything on the screen, but we can see a few, I guess. But if you look at the estimates for B1 and B1 here, you see that they're pretty similar for B2, right? And that's a pattern that kind of persists through the whole parameter estimates. There's going to be one exception. I'm going to mention that here in a second. So what happened when we added this additional hyperparameter is somehow we made our model not run as efficiently, not as well. Doesn't mean that the output was invalid. It just means that it didn't run as well. And so sometimes this can be the difference between a model running at all and not running, of course. Okay, but what is causing this? Okay, well the thing that is causing this is something that we've actually addressed in some earlier video. I don't remember what it is. If you find that, then maybe drop it into the comments. I think it's maybe the first part of this chapter, but I can't remember. But what we've done is we have overparameterized the intercept. Okay, so what do I mean by overparameterize the intercept? Okay, well, we have these different. We have 2 random intercepts. Okay, actually we have. Well, you can almost look at this one as an intercept as well, but we have these 2 random intercepts that we are assigning hyperpriors to. Okay, because so in other words, the intercept is kind of like, what is the baseline level that you expect the outcome variable to take on, and here we're saying, well, it's a combination of these 2 things. That's going to be the baseline expectation, and then the other variables are going to modify that in some way, and both of these now have hyperparameters that need to be estimated. Okay, whereas in the first one, only one of these had a hyperparameter that needed to be estimated. Okay, so we have, in essence, what we have is one value. I mean, it's weird to say one value here, but we have an intercept that is composed of 2 components, but we are trying to estimate 2 things about it. Okay, so we have one thing and we're trying to estimate 2 things about it. So the intuition, I think, is it's as though we've told the model, estimate x and y given this expression, x plus y equals 2, right? Well, we have a lot of different values for x and y that when you sum them can equal 2. In fact, we have infinitely many values that can sum to 2. So this is an intractable problem. The way that our model is actually able to estimate x and y, or the 2 intercept, or the 2 hyperparameters, is because of the priors that actually constrain the solution space. So that's how we can get away with it, but without those priors, on the hyperparameters, we actually couldn't find any sensible answer to this. Okay, so in essence, when we added the gamma bar, what we have done uh, is is to give our computer a much more difficult problem to try to solve, or computationally difficult problem to solve, I guess I should say. Okay, okay. So the last bit that I want to draw our attention to here uh, is um, is going back to these parameter estimates. So we looked at several of these, and they all look to be very, very similar. Okay, um, but there is one notable exception, and that notable exception is let's see if I can get both of them on the screen. Yeah. Okay. Is a bar. Okay. So a bar. The means are a little bit different, but that may or may not be concerning. But when you go over here and you look at the credibility intervals, right? So here's what it is in the first model. But in the second model, that credibility interval is much, much larger. Okay? Why? Well, this again gets back to the x plus y problem, right? We can tweak, if we tweak x up a little bit, then y goes down a little bit, right? So by including g bar in there, so if g bar goes up, then a bar goes down, and if g bar goes down, then a bar goes up. But in other words, what we've done by adding the g bar is we've made it so that a bar has to compensate to the random values, or I shouldn't say random values, but for the plethora of values for g bar. And so that is increasing the credibility interval for a bar. Earlier in the book, there was the left leg, right leg example, which would be a good, maybe provide some good intuition as to how this is happening. But okay. But anyway, I guess we will call that good there.